So in this course, we are going to discuss thermodynamics, and there is a lot of history related to thermodynamics which we will not discuss. But there are some interesting part when it comes to it. We will talk about it. So I'm not going to discuss what is the meaning of the word thermodynamics. It is, I believe, already clear to you. If not, you can check it out on internet. And so I will start with uh, what is known as conservative fields, and why you will see that in a bit. So we'll take an example of work which I will confuse you with first, and then we'll come back to it. So if I take a piece of rough surface and I start from point A to point B and I just scratch it like this, and then I scratch it like that, and then I scratch it, say, like this. So in all three ways, I'm going from point A to point B, but the amount of work which is being done along these paths are not same. So these three are not equal. You can imagine that because when you are scratching on a longer path, you are going to scratch the surface more. So therefore, amount of heat generation, amount of wear to the thing from which you are scratching is going to be more, and therefore more work is being done when you take a longer path. Okay. So in this case, what we can say is that work is path dependent. So it changes when you change the path. But there are cases where the amount of work which you do is path independent. So you take whatever path, the value does not depend on the path, but it depends on the initial and final position. And when that happens, it is called that the field is conservative. So now let us look at the conservative field concept. So a conservative field is described when you have what is known as potential, and the force, or say some variable, in this case force, can be described as the divergence of a potential, or I shouldn't say divergence, but I should say that it is the gradient of the of a potential energy. And this you can realize on a very simple example, that you have a ball kept at a height h1 and you have a ball kept at a height h2. So you have potential energy at these two heights is mgh1 and mgh2, and therefore the force which is applied in this case is simply the derivative of the potential energy. And so this is the force applied, but it doesn't mean that ball will go from h1 to h2. Okay. But when this can happen, when this happens, so this is a scalar quantity. And when this happens, it is called a conservative field. Why it is called a conservative field? What is being conserved here? It makes it path independent, but the conservative nature of the field is described by what is known as Pfaffian integral, which is an old word for that these days, and also the simpler word for this is called exact integrals. So exact integrals in the books of thermodynamics is denoted with a symbol small d, and when you have exact integral, then the forces are conservative, the field is conservative, and the variable is path independent. And when it is not, then you in some textbooks you will see that it is described by a symbol this, and in some textbook it is described by a symbol delta. So not partial derivative, but this kind of delta, not this delta, this delta. So So these kind of integrals are written in this form, p dx plus q dy, and the integration is taken over a path, say from a to b, and it's a line integration. It is not an area integration. And so say that the value of this is g. So that means which is equal to integration of dg from a to b, which is equal to this. So basically dg is equal to this. Okay. And when you use convert this using I think Euler's theorem, I believe, if when you change it to area integration, then this integration converts to del p by del y minus del q by del x dx dy. And dx dy you can write as dA. So it becomes an area integration. So you have double integration. And you see that if it is the criteria for being conservative is that this term will be equal to this term. And when that happens, it becomes 0. Okay. So it really doesn't depend on path. And so the criteria for conservativeness is del p by del y is equal to del q by del x. Okay. So you don't have to think much about it. What you can grasp from this discussion is that there are situations where you have variables which do not depend on the path you take from going from say point A to point B, but it only depends on the initial and final position. And these variables are called state variables because they are only dependent on state. Okay, I'll give you an example of state variable. So one example of work which I discussed was friction. When you scratch the surface, and there the work is an inexact integration, so it is path dependent. But you have work also in other examples where it is not path dependent, and those examples are gravitational forces, electromagnetic forces. Okay, electromagnetic forces. And in these fields, because these fields are conservative, you get laws like P dot dl is equal to some constant. So this is a line integral, and usually in conservative field, when you have a loop integral, that means you have a path which starts from the same point. So from A you go to A, and when you do that, the amount of work done, the line integral is 0 in that case. So the line integral for a closed loop will be equal to 0 for a conservative field. Conservative field. Okay. And in this case, so force can be defined as the gradient of potential energy, and therefore I can write this integral as this dot dr, where u is a function of r. So then that value becomes ub minus ua, negative of that when you apply a and b, and so if you are going from a to a, then that is equal to 0 itself. Okay, but in electromagnetic or gravitational forces, you can have a situation where this line integral is non-zero. And that can happen when the field itself is broken. So you have a singularity, for instance. For instance, in gravitational field, you have a black hole. So in that case, actually what you have is a source or sink of energy. So you can imagine this as a heat field where you have a source of heat. So the line integral is finding out that how much amount of potential energy changes, but then you have additional, so it cannot be zero even if you come back to the same point, because you have something inside which is creating heat with a rate. So that amount of energy comes in. So in that case, it will be non-zero. So you will have F dot dr plus minus some energy, and that will be equal to zero. And it depends whether the heat is being, so the energy is being absorbed or it is being consumed. It is being given out. Okay. So with this concept of state variables, now that I believe you have some idea and the understanding of state variable, we can come to what is known as the first law of thermodynamics. So, so first law of thermodynamics is simply the balance sheet of the expenditure which we do. So whatever comes in goes out kind of thing. So it's a balance sheet, debit and credit. And what it tells is that basically the total amount of energy, the total amount of funds you have been given. If you do not have a source of other income, then the total amount of uh, earning you are getting must be equal to the expenditure plus savings. Okay, whatever you're not spending has to become savings, and that amount has to match with the amount which you are earning. So that is what it is. So this is why it is also known as bookkeeping law. Okay. So, and you will see that this law is written in this form where you have exact integral, so which is equal to summation of two inexact integration. It is not always true that one exact integral quantity will be equal to two inexact integral quantity, but in this case it happens like that. And there are other cases also where you will see similar things happening. So I'll give you an analogy, but that is only an analogy. It is not in direct correlation with it. Well, there is a thermodynamics background to that, but we'll see. So, so du is equal to, du is internal energy, change in internal energy, is equal to the amount of work done by the system or on the system plus the amount of heat which is absorbed or given by the system. So if the system cools down, that means the work is being done on the environment, and if the system heats up, that means the work is being done on the system. Okay. So that is what it is, and there are different conventions people follow. Some people take the amount of work done on the system as positive, some people take it as negative. It doesn't matter. So you can call expenditure in positive and savings in negative and vice versa. It doesn't really matter that much. You just have to follow the same convention. Don't change the convention in the middle of the understanding somewhere. So this is what basically first law is. So it doesn't matter that you are changing the internal energy from point A to point B. U is a state variable. Okay. So it doesn't depend on path. It's a state variable. Work sometimes can be state variable, sometimes it is not a state variable. And heat is also not a state variable. So heat changes, the amount of heat changes when you take different paths. So you can also write it in different ways. So dq is equal to du minus dw. What does that mean? It means that if you give some amount of heat to the system, that amount of heat will change the internal energy for the system. So say that the amount of heat which I'm giving to the system, I take that as positive. Then that amount of heat goes into changing the internal energy of the system, and then it can also be used in doing some work. Okay. And that is the work which is being done by the system on the environment, which is taken as negative here. Okay. So when uh, system does work, then we take that as negative. When the work is done on the system, we take that as positive in our convention. You can take it otherwise also. So, so when you supply some energy to the system in the form of heat, you can also write it in dW form. So when you say do some work on the on some system, so you have a piston kind of thing, and you have a gas in it. Okay, so you have a gas in it, and you compress it. Okay, you push the piston down. So you have done some work on the system. So it started from this point and you compressed it to this point P. So you have done some work on the system, right? So that is positive. So this is positive. And this amount of work which has been done on the system will change the internal energy of the system. Okay. And it will also change the heat of the system. So when it is compressed, the matter here will heat up. Okay, because you have less volume now for gases to collide with each other, and they have kinetic energy, so there will be more collision, and therefore the internal energy will change and the amount of heat will also change. And you can then create a constraint. Okay, you can create a constraint where you say that the heat I'm not allowing to go in or out, which is called adiabatic system. Adiabatic system in reality can be made with good precision, but usually it appears in very fast processes. And when I say fast and when I say slow, these are very relative terms. So the concept of time and the concept of fast, how fast things are and how slow things are, that will have to develop during during this course. And one idea which came by this piston thought process is that leads to the second law of thermodynamics, which we will not discuss right now, but I'll just give you the glimpse of it. So in the thought experiment, you have a piston, so you have a wall which is movable. Okay, so you have this piston and you have this wall which is movable, and you have a gas in it, and so outside the pressure is zero. Okay, so it's vacuum. Inside you have a gas, so you have some pressure in it. Okay, so if you put the system in the vacuum, what is going to happen to this lid? This was the question which is being thought by Lord Kelvin. Okay, and and what you think is that because you have some pressure, it is going to move the piston up because the other walls are not movable. Okay, so gases are going to collide with the lid, and they are going to apply some um, forces in the form of pressure, and the amount of work which will be PdV, because there is a pressure which will, so P will be a function of volume. Okay, so as the volume changes, as this piston goes up, now you see that you have, say, 10 atoms of gases here. So these 10 atoms of gases are now having a bigger room. So they are not going to exert that much pressure. And what is pressure is that average number of collision which is happening on this wall. Okay. So if you have less number of people in the train, then of course they're going to move, and they're going to do all sort of things. But there are less probability that one localized region will have any effect from smaller number of people, and this pressure will keep on decreasing as the lid goes up. Okay, so what Lord Kelvin thinks is that will it stop at some point? So there will be a scenario when volume will be so large that, so okay, so now let us think that we have only one atom. Okay, so instead of 10 atoms, we have only one atom here, only one single atom. Okay, and now the single atom is colliding on all the boundaries, and of course on this wall also. So and as and when it hits the wall, it pushes the wall a little bit on the other side, because there is nothing stopping on the other side. The pressure is zero, so the lid keeps on moving up and up. We're not talking about how fast the lid is moving. Okay, so but it is moving. Nobody is stopping that to happen. And then Kelvin thinks that, will it stop ever, or will it keep on moving the lid until eternity? And that's when the idea comes that there will be a time when this atom will have no tendency to hit anything. Okay, and that creates an absolute scale of another property, which we will discuss when we talk about the second law of thermodynamics. So keep this thing in mind, and we'll come back to that. So with state variable and the bookkeeping law, now we have to discuss what is known as intensive and extensive properties. So intensive properties are those properties which are not dependent on the mass of the system. So it's like the story Andher Nagari Chaupat Raja. So 1 kg potato has the same price of 1 kg gold. So if so, 2 kg gold is also having the same price. 10 kg gold is also having the same price. So that means there is something which does not change even if you change the mass of the system. So whatever is happening for 10 atoms is same for 100 atoms, it's same for 1000 atoms, and so on. Can you think of some properties? I believe you can. So one is temperature. Okay. So temperature does not depend. So if you have 20 liters of nitrogen gas, you put 50 liters of nitrogen gas into it, which is at the same temperature, it will not add up, and the temperature will not double up, right? The mass has doubled. What has doubled is also volume, right? So volume is an extensive property, and temperature is an intensive property. What is an intensive property is also pressure. Pressure will also not add up, okay? And an extensive property can be made intensive when you make it per unit mole. Okay. So what is known as molar volume is volume divided by number of moles uh, in the system. Then that becomes intensive. So that does not change. Okay. Volume is increasing because you are putting more number of moles in the system. Okay. So this was very simple, and then experimentally it was found that at very low pressure, it was found that pressure into volume followed a hyperbolic equation. So at very low pressure, when you keep a gas, and we're talking about gas right now, gases. So if you keep the in the low pressure regime, if you change the pressure, and the volume changes. Okay, so pressure and volume has a relationship, and this relationship is hyperbolic. Okay, so when you plot pressure versus volume, it is hyperbolic, so it follows this kind of equation. Okay, so at any point, if the pressure is high, the volume is low. If the pressure is low, the volume is high, and this quantity PV is approaches constant value. Okay, but it depends on number of moles and temperature. So then what is known as ideal gas law. So that means if you plot NT, so PV divided by number of moles and the temperature of the system, that approaches a very peculiar kind of value, 8.314, and that is known as universal gas constant. Universal, sorry, universal gas constant. Okay, and you see that you also get another universal constant in another conservative field where you have gravity. Okay, in Newton's law, you get the gravitational constant G, which is a universal constant. That comes in a conservative field of gravitation. This comes in the conservative field of pressure and volume. So pressure multiplied by volume, if you look at the unit of that, what is the unit of that? So pressure is force per unit area, right? So that is megapascal. Pressure is Newton per millimeter square or meter square. So Newton per meter square. And volume is meter cube. So this is Newton meter, which is joules. It comes from Joule's law actually. And this is the unit of energy. Okay. And you see that PV acts like a potential energy. It's a kind of energy. It has a unit of energy. Okay. So this is known as PV is equal to nRT, is known as ideal gas equation, and there is why it is called ideal. Anything ideal, ideal government, um, ideal person, ideal relationship does not exist, right? Similarly, there are no gases which are ideal. It is an idealization. At low pressure, gases do follow very close to this law, but in reality, it is not. So why? Because the derivation of this ideal gas equation does not take into account the interaction of one gas atom with another atom. Okay. So this was further modified by uh, some other people, and you have a very not that complicated equation, but you have a variation of ideal gas equation. It's something like n by v some constant plus n by v whole square, another constant, and so on. So this is a generic equation which creates the relationship between pressure, volume, and temperature. And these three variables, when you have the equation correlating these three variables, are known as equation. If you have one equation, if you have more equations, then called equations of state. Okay. And this B1 and B2 and so on are called virial coefficients. Virial coefficients. And one example of breaking this ideal equation is when van der Waals equation. Okay, and what he does is just goes from 1 to 2. So he says that two atoms will interact with each other, and when that happens, the volume decreases by a quantity B. Okay, N is number of moles. So volume decreases and pressure is also reduced because of the interaction of two atoms with each other. So pressure is given by nRT divided by V minus NB plus N by V whole square. And why N by V whole square is because mole per unit volume, you have one atom, so two atoms. When the two atoms are interacting with each other, then the probability of interaction is proportional to N by V square. Okay, so that's why you get in this expression you get other terms like n by b whole cube and so on. So you have three atoms interaction, four atoms interaction, and so on. So, so this is van der Waals equation of state for gases where the the interaction between two gaseous atoms are considered. It is also not a real case, but it is better than ideal gas equation. A little bit better than ideal gas equation. Okay, and here B is greater than 0.